Hello, my name is Kevin Davis, and this is my lab report for Lab 4, Oscillations. To introduce, the purpose of this lab is to observe the motion of a spring mass system with the mass stretching and compressing to form an oscillating arc pattern experimentally on tracker, then plugging the data into a computational model to see if it follows the energy principle, that computational model being GlowScript. The fundamental principles of physics demonstrated in this lab include Newton's second law, or the momentum principle, position update, saying that the final position is equal to the initial position plus the average velocity times the change in time. The velocity update formula, final position equals initial position plus F net over the mass times the change in time. The energy principle, E of system equals Q plus W. Spring force, force equals negative K times L minus L initial. Kinetic energy, energy of kinetic equals 1/2 mass times velocity squared. Gravitational potential energy, UG equals negative big G, capital M, lowercase m, divided by R. And then spring potential, which is 1/2 K times L minus L 0 squared. The lab procedure is as follows. Part 1, we will observe the motion of a spring mass system in 2D with compression and stretching from the spring in an oscillating arc pattern, using the tracker software to find the observed position. Part 2, we will determine if the model follows the energy principle on GlowScript and then compare the two. This was my tracker experimental software. As you can see, I have the calibration stick set to the right height shown in the pre-lab videos. On the side is the position time graphs for both the X and the Y, and then on the far right is the data from tracker pulled and put into the excel.csv file. Now, after analyzing the tracker data, we find that the initial position is negative 1.2, negative 0.628, 0 meters, and since the spring begins at rest, the spring mass system, its initial velocity will be 0 meters per second. Additionally, in the pre-lecture videos, video 51 shows that the initial compression distance of the spring is 0.15 meters, the mass of the spring mass system is 0.402 kilograms, and that the spring constant is 6.87 newtons per meter. Here is the code for the GlowScript or computational model. As you can see, I put the mass of the ball here, the initial position at the ball dot position, and then the velocity vector is 0, 0, because that's the same as the initial. The gravitational constant, 9.8 meters per second, is here. Spring constant, 6.87, and the initial spring position, the relaxed length of the spring, are given here in the code. Additionally, we find what L is, L hat, and then also S, which is the difference between the magnitude of L minus the initial position. Shown at the bottom are the formulas for the energies. And then over here is the potential, the spring, and the net force all factored in. Here is the result. The experimental model, which is in red, follows close to the computational model, which is in blue, in the X position, as you can see on the top graph. And then, although it has a similar peak on the Y graph, the dip does not go nearly as low in the Y position. Does it follow the energy principle? Yes, it does follow the energy principle because energy remains constant. As you can see on the graph, the yellow line, delta E, or the change in energy, remains 0. And then since there are no external factors, that is why the change in energy on the graph is 0. Now, what are some potential sources of error that could have caused these results? 1, human error, such as tracking the center of mass on tracker, as well as the calibration stick. And then 2, the system is not completely isolated. In the video, potential work could be done by other forces. Now, lastly, we are asked to compare the oscillation periods between the X and Y coordinates. Now, taking the X direction, we subtract the peak minus a dip to find the difference in time being 0.224 seconds. And then in the Y direction, we see that it's very similar, being 0.128 seconds, which does make sense following the energy principle since they would need to have similar times.